Welcome back. In this video, we're going to look at examples of representing functions as Taylor series and Maclaurin series. Let's get to it. All right, so here's our first example. We want to find the Taylor series centered at c equals 1 for the function f of x is equal to the natural log of x. Okay, and so in order to find a Taylor series centered at c equals 1 for this function, we first need to know what a Taylor series looks like. And so remember, a Taylor series is a series where we have the sum from n equals 0 to infinity of the nth derivative evaluated at c divided by n factorial times the quantity x minus c to the power of n. All right, so a Taylor series is just a different form of a power series. We still have that x minus c to the power of n, which means that this is a power series, but more specifically, it's a Taylor series. And then, of course, a Maclaurin series is just a Taylor series where the value of c is 0. So we have the nth derivative evaluated at 0, and we have x minus 0 to the power of n, which is just x to the power of n. And so a Maclaurin series is simply just a Taylor series where c is equal to 0. Okay, and so in order to represent the natural log of x as a Taylor series centered at c equals 1, what we will need to do is find a way to represent the nth derivative of that function evaluated at c. All right, and so in order to do that, we need to start finding the derivatives of our function. Right, we want to find the first derivative, the second derivative, and some other higher order derivatives and see if we can see a pattern for those derivatives and represent them as an nth derivative for this function. All right, so we have f of x is equal to the natural log of x. Now the derivative, f prime of x of the natural log is 1 divided by x. Okay, but we can rewrite that by moving x to the numerator and giving it a negative exponent. And so instead of having 1 divided by x, we could move x up to the top and have x to the power of negative 1. So I'm going to rewrite this. The derivative of the natural log of x could also be written as x to the power of negative 1. All right, then if we look at the second derivative of our function, f double prime of x, that will be equal to the derivative of x to the power of negative 1. Now we can use the power rule for derivatives here and multiply our exponent down and then subtract 1 from that exponent. So negative 1 multiplied down will give us negative 1 times x to the power of negative 2 because we subtract 1 from this exponent, and negative 1 minus 1 is negative 2. Okay, now f triple prime of x, the third derivative, will be equal to the derivative of the second derivative. So we'll multiply that exponent down again, and we'll have negative 2 times negative 1. So those negatives will cancel out, and we'll have 2 times 1 times x to the power of negative 3, because we subtract 1 from that exponent again. And then let's do another derivative. Let's look at the fourth derivative. And the fourth derivative will be the derivative of the third derivative. So we'll multiply this exponent down again. And so we'll have negative 3 times 2 times 1 times x to the power of negative 4 because we subtract 1 from that exponent again. All right, and I haven't been simplifying what these look like because remember, we're looking for a pattern to represent the nth derivative. Okay, now I want to take a look at another derivative, so let me clean up my work a little bit here. If we take one more derivative, we'll have the fifth derivative of x is equal to the derivative of the fourth derivative. So we'll multiply negative 4 down, and that negative will cancel out with this negative. So we're just going to have 4 times 3 times 2 times 1 times x to the power of negative 5 if we subtract 1 from that exponent of negative 4. Okay, and so now that we have 5 derivatives, hopefully that is enough for us to see a pattern in our derivatives that we can represent as the nth derivative. All right, so what could we say that the nth derivative of x is equal to based on these first 5 derivatives? Well, the first thing I notice is that for each of these derivatives, we have x raised to a power, where that power is the negative version of the value of n that we would be working with. Right, so we would say that the first derivative is when n equals 1, right? So when n equals 1, the nth derivative would be the first derivative of x. So when n equals 1, we have x to the power of negative 1. Then when n equals 2 for the second derivative, we have x to the power of negative 2. When n equals 3 for the third derivative, we have x to the power of negative 3. And then for the fourth derivative, we have x to the power of negative 4, and so on. All right, so we know for a fact that our nth derivative is going to involve x to the power of negative n. Whatever that nth derivative is that we want to find, we're going to have x to the power of negative n in that derivative. All right, now that's not the only thing that we can find in our derivatives. What I also notice is that the signs of our derivatives are alternating, right? The first derivative is positive, the second derivative is negative, the third derivative is positive, the fourth derivative is negative, and the fifth derivative is positive. All right, and so we can represent that in our nth derivative by including negative 1 to the power of n plus 1. All right, and I chose the power of n plus 1 because our first derivative is positive, so when n equals 1, we'll have 1 plus 1, which will be squaring negative 1, which makes sure that that first derivative is positive, and then our terms will alternate from there. All right, when n equals 2, we have 2 plus 1, so we have the power of 3, and negative 1 to the third power is negative 1, so when n equals 2, that's the second derivative, we will have a negative derivative. All right, so that takes care of the signs of our derivatives, but now there's one more thing that we need to take care of, and that is the coefficients, or these constants that are being multiplied by x to the power of negative n. Right, so notice that for the fifth derivative, we have 4 times 3 times 2 times 1. That would be the same as 4 factorial. For the fourth derivative, we have 3 times 2 times 1. That is the same as 3 factorial. And then for the third derivative, we have 2 times 1. That would be the same as 2 factorial. And then for the second derivative, we just have 1. And so you could say that 1 is the same as 1 factorial, because 1 factorial is just 1. And then for our first derivative, we also have a coefficient of 1. I just didn't explicitly write it, but we would have 1 times x to the power of negative 1. And we could say that that is 0 factorial. All right, 0 factorial is also equal to 1. So what we find here is that given a certain derivative, the coefficient of the derivative will be some factorial where the number for that factorial is 1 less than the value of n for the derivative. Right, for the fifth derivative, we have 4 factorial. 4 is 1 less than 5. For the fourth derivative, we have 3 factorial, and 3 is 1 less than 4. And then in the third derivative, we have 2 factorial, and 2 is 1 less than 3. And so you can sort of see the pattern here. Our coefficient is always going to be represented by n minus 1 factorial. And so now we have an nth derivative that represents all of these derivatives. For any nth derivative that we would want to find, we just plug in our value of n into this expression, and we will find that derivative. Okay, but this isn't quite what we want for our Taylor series, right? In order to express the natural log of x as a Taylor series, specifically a Taylor series centered at 1, what we have to do is evaluate the nth derivative at c. And so, since we want a Taylor series centered at c equals 1, all we have to do is plug 1 into our nth derivative, and then we will have this part of our Taylor series, and we can write the natural log of x as a Taylor series. Okay, so if we plug 1 into the nth derivative, what will that be equal to? Well, if we look at our nth derivative here, there's only one x to plug a value into. Everything else is expressed in terms of n. So we would have 1 right here, and 1 to the power of negative n would just be equal to 1, right? 1 to the power of anything that's finite, meaning it's not infinity, is just going to be equal to 1. 1 squared is 1, 1 cubed is 1, 1 to the power of negative 2 is 1, 1 to the power of anything is 1. And so that will just become 1, and we'll be left with the rest of our nth derivative in terms of n. So our nth derivative, evaluated at 1, will be negative 1 to the power of n plus 1 times n minus 1 factorial. Okay? And so we can represent the natural log of x with a Taylor series by just replacing this part of the general form of a Taylor series with our nth derivative evaluated at 1. And then we also need to remember to replace this c in x minus c with 1 as well. And so our Taylor series will look like this. The natural log of x will be equal to the sum from n equals 0 to infinity of the nth derivative evaluated at 1, which we now know is negative 1 to the power of n plus 1 times n minus 1 factorial. and that will be divided by n factorial and multiplied by x minus c, which is 1 to the power of n. Okay, and so this Taylor series right here will represent the natural log of x. However, we can simplify the series a little bit, so if I clean up my work, notice that we have a factorial in the numerator and denominator, and so we can actually cancel that out because we can rewrite n factorial in such a way that it will cancel out with the numerator. And here's what I mean by that. We can rewrite n factorial to be n times n minus 1 factorial. Right? For example, if we had 4 factorial, that's equal to 4 times 3 times 2 times 1, but that would also be equal to 4 times 3 factorial, because 3 factorial is 3 times 2 times 1. So we can subtract 1 from the value of our factorial, multiply the original value of our factorial by that value that is 1 less, and then have the factorial there. So n factorial would be the same as n times 1 value less than that value factorial. All right, and so we can rewrite our denominator to be n times the quantity n minus 1 factorial. So if we do that, the natural log of x will be equal to the sum from n equals 0 to infinity of negative 1 to the power of n plus 1 times n minus 1 factorial. And then I'm going to move this quantity into the numerator. So we're going to have x minus 1 to the power of n divided by n factorial, which is now n times n minus 1 factorial. And now we have n minus 1 factorial in the numerator and denominator. And so those are going to cancel out and leave us with the sum from n equals 0 to infinity of negative 1 to the power of n plus 1 times the quantity x minus 1 to the power of n divided by n. And this is the Taylor series centered at c equals 1 for our function, the natural log of x. The only thing left to do at this point is determine the interval of convergence for this series. But because that's not the focus of this particular video, in this video we're just looking to find Taylor series and Maclaurin series, I'm not going to go through the ratio test step by step for this power series because that's what you would need to use to find the interval of convergence. Instead, I'm just going to put the work up here on the screen for you, and you can see how the ratio test would be done for the power series or the Taylor series that we just found, and you would see that the series converges for the values of x from 0 to 2, including 2. And I didn't show the work here of checking the endpoints, so hopefully you were able to check that for yourself if you're interested. But if you're not familiar with checking endpoints when you're using the ratio test for power series, be sure to watch my video on power series and the interval of convergence. I'll have that video linked in the description below. Okay, so feel free to pause the video and look at this work of the ratio test for our series, but just know that the Taylor series we found converges for this interval of convergence from 0 to 2, including 2. And so with that, this is the Taylor series centered at 1 for our function, the natural log of x. Let's take a look at another example. All right, so here's our next example. We want to find the Taylor series centered at c equals 2 for f of x is equal to e to the power of 3x. Okay, so if we want to find a Taylor series for this function, we want it to be in this form of the sum from n equals 0 to infinity of the nth derivative evaluated at c divided by n factorial times x minus c to the power of n. All right, but now in this case, our value of c is 2. So really what we want here is our nth derivative evaluated at 2 and x minus 2 to the power of n. So I'm going to rewrite that and replace c with 2. Okay, so this is the form of the Taylor series that we want for this function. And in order to complete this series, we need to find the nth derivative evaluated at 2 for this function. So what we have to do is start taking derivatives of this function. All right, so we have f of x is equal to e to the power of 3x, and the first derivative, f prime of x, will be equal to the derivative of e to the power of 3x. Now the derivative of an exponential function with a base of e will just be equal to that exponential function, e to the power of 3x, and then we need to multiply by the derivative of that exponent via the chain rule. All right, now the derivative of 3x is just 3, so we're going to multiply by 3. So 3 times e to the power of 3x is the first derivative of this function. Okay, and so now the second derivative, f double prime of x, will be equal to 3 times the derivative of e to the power of 3x, which once again is 3 times e to the power of 3x. Every time we take the derivative of this function, that exponential part is going to stay the same, and we're just going to keep on adding another constant multiple of 3, right? We're just going to keep multiplying by another 3 each time, because when you take the derivative of e to the power of 3x, the chain rule says we need to multiply by the derivative of that exponent, which is always going to be 3. So the third derivative, f triple prime of x, will be equal to 3 times 3 times 3 times e to the power of 3x, because these two 3's carry over, and then the derivative of e to the power of 3x is 3 times e to the power of 3x. Okay, now we could go on forever. I could write out the fourth derivative, the fifth derivative, and so on, but by this point, I think we can see the pattern that's happening with our derivatives, right? We could say that the nth derivative of our function will be equal to 3 to the power of n times e to the power of 3x, right? We're always going to have that e to the power of 3x in every single derivative, so we have that right here. But then depending on the derivative, we're going to have a certain amount of 3's. In the third derivative, we have 3 3's, so we would have 3 cubed for the third derivative when n equals 3. For the second derivative, where n would be equal to 2, we have 3 squared, we have 2 3's. And for the first derivative, we have 1 3, and so we would have 3 to the first power. So whatever nth derivative we would want to find, the number of 3's that we will have multiplied by e to the power of 3x will be determined by that value of n. All right, so the fourth derivative, we would have 3 to the fourth power. The fifth derivative, we would have 3 to the fifth power, and so on. Okay, so our nth derivative will be equal to 3 to the power of n times e to the power of 3x. Now all we have to do is evaluate this nth derivative at the value of 2. That's our value of c. Okay, and so if we do that, the nth derivative evaluated at 2 will be equal to 3 to the power of n times e to the power of 3 times 2. The only x that we needed to replace with 2 is this x right here. So we have e to the power of 3 times 2, and 3 times 2 is equal to 6. So our nth derivative evaluated at 2 will be 3 to the power of n times e to the power of 6. Okay? So we can replace the nth derivative evaluated at 2 with this expression and represent our function as a Taylor series. Okay, and so if we do that, our function f of x, which is equal to e to the power of 3x, will be equal to the sum from n equals 0 to infinity of the nth derivative evaluated at 2, which is 3 to the power of n times e to the power of 6 times x minus 2 to the power of n divided by n factorial. Okay, now in this case, there's nothing to simplify here, and so this right here is the Taylor series centered at c equals 2 that represents this function. E to the power of 3x is equal to this power series. All right, and then just like our previous example, you would also want to find the interval of convergence for this power series. And in order to do that, you would need to use the ratio test on this series, but that's not the focus of this video. So once again, I'm just going to put that work up on the screen here, and you can pause the video and look over this work to see how the ratio test would be done for this particular series. But in the end, you would find that this series converges for all values of x, so the interval of convergence would be from negative infinity to infinity, because the result of the limit for the ratio test is always going to be 0, which is always less than 1, which from the ratio test means that the series converges for all values of x. All right, and once again, if you're not familiar with the ratio test for power series, be sure to check out my video on power series and their interval of convergence. I'll have that linked below if you're interested in seeing that. Okay, but feel free to pause the video and look over this work if you're interested, but just know that that power series or that Taylor series that we found for our function converges for all x. So negative infinity to infinity is the interval of convergence. Okay, so you could write that down, that this is convergent from negative infinity to infinity, but I had it written on the other page. Either way, make sure to make a note of this in your own work if you're following along. Okay, and so that's the end of this example. And now we're going to look at a couple more examples, but they're going to be a little bit different than the first two. In these first two examples, we have created a Taylor series completely from scratch. We started with just a function and we wrote out our derivatives. We found an nth derivative and then we used that to represent our function as a Taylor series. But with the rest of our examples, we're going to be finding Maclaurin series, which are Taylor series centered at 0, and we're going to be representing functions as Maclaurin series by using already established Maclaurin series that we are familiar with. All right, and so let me show you what I mean. Here we have a list of some common Maclaurin series that we can use to represent functions similar to these functions right here as Maclaurin series, which once again are just Taylor series centered at 0. Okay, and these are just a couple of the common Maclaurin series that you might run into. I give you a couple more in my lesson video, so be sure to check that out. I believe I have the arcsine function and the arctangent function included in that video. But for this video, we're just going to need this list right here. In fact, we're not even going to use all of them. We're just going to use a couple. But what we can do is easily find Maclaurin series for functions similar to these series by just using these already established Maclaurin series for those functions. And in most cases, the intervals of convergence are also going to be the same for those functions. They have already been found for these power series, and so there's going to be no need to use the ratio test. The only time where the intervals of convergence may be different for a certain series is when you want to represent a function as a Maclaurin series similar to one of these functions where the interval of convergence is not negative infinity to infinity. When you have negative 1 to 1 or negative 1 to 1 including 1, sometimes those endpoints could change depending on what is replacing x in the functions similar to these functions. And we'll take a look at that with one of our examples. I'll show you what I mean when we get to it, but for now, just know that if you're representing a function as a Maclaurin series that's similar to e to the power of x, sine x, or cosine x, where the intervals are just all values of x, then that interval of convergence will not change. All right, and so with that, let's take a look at our first example of using these common Maclaurin series to find a power series or Maclaurin series representation of similar functions. Okay, so here's our next example. We want to find the Maclaurin series for f of x is equal to x times cosine of 4x squared. All right, now remember, a Maclaurin series is just a Taylor series centered at 0. And when you are asked to find a Maclaurin series for a function that is similar to a function that we know the Maclaurin series for, then you can use that known Maclaurin series to take a shortcut and easily represent this function as a Maclaurin series. We don't have to start from scratch, right? This function here has cosine within it. It's similar to the cosine function. It's a little bit different because we have x times cosine of 4x squared, but we can actually use the Maclaurin series for cosine to easily represent this function as a Maclaurin series. All right, so from that list that we were just looking at, we saw that cosine of x is equal to this Maclaurin series. We have the sum from n equals 0 to infinity of negative 1 to the power of n times x to the power of 2n divided by 2n factorial. All right, and that's convergent from negative infinity to infinity. Okay, and so this is the Maclaurin series for cosine of x, but how can we use this for this function where we have an x multiplied by cosine and we have cosine of 4x squared, not just cosine of x? Well, what we can do is actually replace that x with 4x squared and also replace it within the series. Right? What we can say is that cosine of 4x squared, and don't worry, I did not forget about this x, we'll come back to that in a little bit, but what we can say is that cosine of 4x squared will be equal to the sum from n equals 0 to infinity of negative 1 to the power of n times x to the power of 2n, but this x will be replaced with 4x squared, since that is what x now is. All right, so we're going to have 4x squared to the power of 2n divided by 2n factorial. Now we can simplify a little bit. We can take both 4 and x squared to the power of 2n. So this would be equal to the sum from n equals 0 to infinity of negative 1 to the power of n times 4 to the power of 2n times x squared to the power of 2n. But taking x squared to the power of 2n would be the same as multiplying those exponents. So we would have 2 times 2n. okay? And then that would be divided by 2n factorial. Now 2 times 2n will be 4n, so I'm just going to erase that, and we will have 4n as our power of x, and now we're almost done, right? This power series right here, or this Maclaurin series, represents cosine of 4x squared. But that's not quite the function that we have, right? We also have this x out front, and so this is actually really easy to account for. All we have to do is multiply our power series by x, right? So if we multiply x by cosine of 4x squared, we'll just multiply this power series by x, and that x will just be combined with this x to the power of 4n. The exponents will be added. If we multiply our series by x, I'll do it right here, we have x to the first power times x to the power of 4n, so we could combine those by adding their exponents, 4n plus 1. So I'll just erase that x, and we'll add 1 to that exponent, and now this power series, or this Maclaurin series right here, represents this function, x times cosine of 4x squared. And just like the original Maclaurin series for cosine of x, this will also be convergent for values of x from negative infinity to positive infinity. Okay, and so that is why knowing common Maclaurin series can be very helpful. If you know what cosine of x is equal to, as a Maclaurin series, you can use that series to easily represent a function involving cosine as a Maclaurin series. All right, and so that's it for this example. And so let's take a look at another example of using a common Maclaurin series. All right, so here's our next example. We want to find the Maclaurin series for f of x is equal to the natural log of 1 plus x cubed. Okay, now this function is similar to a function that we do know how to represent as a Maclaurin series from that list from earlier, right? One of our common Maclaurin series is the natural log of 1 plus x. We know that that is equal to the sum from n equals 0 to infinity of negative 1 to the power of n plus 1 times x to the power of n divided by n, and that series is convergent from negative 1 to 1, including 1. Okay, so you can see the similarities between this function and the function that we want to represent as a Maclaurin series. All we have to do is change this x here and here with x cubed. All right, so what we'll have is the natural log of 1 plus x cubed is equal to the sum from n equals 0 to infinity of negative 1 to the power of n plus 1 times x cubed to the power of n divided by n. All right, all we had to do was replace this x with x cubed because that's what x is in our function. Everything else is the same. We have the natural log of 1 plus x, but now we have the natural log of 1 plus x cubed, so we replaced that x with x cubed. Now we can simplify a little bit. X cubed to the power of n will just be x to the power of 3n because we multiply these exponents to get the new exponent for x, right? So instead of having x cubed to the power of n, we will just have x to the power of 3n. All right, and then this series will actually share this interval of convergence, which is from negative 1 to positive 1, including positive 1. All right, and now you would want to check that in this case because the interval of convergence for our common Maclaurin series that we're using is not from negative infinity to infinity. You're going to want to check to make sure that this is still true. All you have to do is remember that for this series, what we're saying is that when x is between these two values, including 1, that it converges. So for our common series, we have x less than or equal to positive 1, but greater than negative 1 is when this series converges. And so all we have to do is replace this x with what it is now in this function that we're trying to represent as a Maclaurin series. So all we'd have to do is look at negative 1 less than x cubed less than or equal to 1. We just replaced x with x cubed. And then you would just want to solve for x. So we would take the cubed root of all parts of this inequality, and the cubed root of negative 1 is negative 1, the cubed root of x cubed is x, and the cubed root of 1 is 1. So we're still going to have negative 1 less than x less than or equal to 1, so the interval of convergence stays the same. However, let's say that instead of having x cubed, let's say that we had the natural log of 1 plus x cubed divided by 8, right? Let's say we had some constant multiple within there as well. then our interval of convergence is going to change. Because now instead of replacing x with x cubed, we have to replace that with x cubed divided by 8. So if we do that for this little example here, if we replace x cubed with x cubed divided by 8, then we need to multiply every side by 8, and that will give us negative 8 less than x cubed less than or equal to 8, because negative 1 times 8 is negative 8, and 1 times 8 is 8. And now if we take the cubed root of each part, the cubed root of negative 8 is negative 2, the cubed root of x cubed is x, and the cubed root of 8 is 2, and so that would give us negative 2 less than x less than or equal to 2, which in interval notation is negative 2 to 2, including 2. All right, so that's how the interval of convergence would change if that replacement for x involves some constant as well. But if you don't have a constant, it's most likely the case that the interval of convergence will remain the same. But it never hurts to check if you want to make sure that you have the right answer. Okay, but the most important takeaway here is that you do not need to use the ratio test when you use a common Maclaurin series to find the Maclaurin series for a function. All right, since we already know that this series was convergent from negative 1 to 1, including 1, we could use that information for this Maclaurin series that represents our function. And let me just rewrite this back to what it's supposed to be. Instead of x cubed divided by 8, we should just have x cubed. Okay? And so this is the final answer for this example. All right, and so with that, this was the last example for this video. And so if you have any questions, feel free to leave those in the comments below. But if you don't have any questions, this is all I had for now. So I will see you next time.